Hello, everybody. So what we're going to be looking at today is section 6.3 in the book. That is conservative vector field. Now, we've already talked a little bit about conservative vector fields. So a lot of this is actually going to be stuff that we talked about um, in section 6.1, and we're just going to be reminding you of it. So that's nice, makes it a little bit easier. And also this section is not particularly difficult at all, really. So um, with that said, we'll get right into it. What we're going to talk about is what are simple and closed curves and regions. Um, that'll be really simple. Just look at some pictures. We're going to explain how to find the potential function for a function for a vector field, which we've already actually done. So it'll just be doing it again. We are going to use the fundamental theorem for line integrals. Now, fundamental theorem for line integrals is actually easier. It's an easier way to do line integrals than we've already done. So that means that we're going to be learning a shortcut here to what we did last time. So that's nice. And lastly, we're going to learn how to test if a vector field is conservative or not, which is also straightforward. So everything we're doing today is, relatively easy. This is not one of the more difficult topics in the class. So let's go ahead and get started. I am going to just draw some pictures and actually draw some pictures. I'm going to steal some pictures just to make it easier on me and make this go a little bit faster here. So let's talk about this. So here's the definition of, actually, let's move this down a little bit and let's say where we're starting here. We are starting with the first topic there, which is going to be curves and regions. Okay, so the definitions are going to match up with your intuitive sense. So, like, forget the definition. Let's just look at these pictures. So they say that this is simple, but not closed. Now, we don't know what simple means yet, but it's obviously not a closed curve, right? Because the ends don't connect. Now, this they say is simple and closed. Well, obviously it's a closed curve, right? That's easy to see. Simple, we don't know what simple means yet. Now, here they say this one is closed, but not simple. And you see it's a figure eight. So, yes, it's closed. And they say it's not simple. Probably you can guess at what simple means now, right? So, simple is going to mean it can't cross itself. And here they say this is not simple and not closed. So the ends are not connected, so it's not closed, and it crosses itself, so it's not simple. Um, so that's really it, right? So simple is going to mean uh, does not cross itself, and closed is going to mean it's a closed curve, right? Closed curve. So pretty simple. If you look up here at the definitions, they're going to say what they mean mathematically by that. So they say it's closed if you can parameterize it so that R of A equals R of B. So, like, the idea is this: you start somewhere, that's R of A, you end somewhere, that's R of B, and if you have a closed curve, you can actually make those the same place, right? Because if you head off in one direction, you're going to eventually come back around and end up at the same place. So that's what closed means. And also, they say for the definition, we want the parameterization to traverse the curve exactly once. That way, you wouldn't be able to call this, well, never mind. But we wouldn't want to, they want it to be possible to have one revolution around the curve being the parameterization. I don't know where that would really be relevant, but we could have it. So, okay, so that makes sense. And then they say curve C is simple if it does not cross itself. Okay, so they just say the words does not cross itself. Um, or they say there's a parameterization of the curve that is one-to-one. So if it's one-to-one, that means none of the points are repeated, which stops this from happening. Okay, except for the possibility that R of A equals R of B. So like here you have a dot and you can say that's R of A and it's R of B. And this next curve does not meet that definition, because if you call this R of A and it's R of B, maybe that could be R of A and R of B. But if you think about starting here, R of A hits it a second time, hits it a third time, right? If you want to go around the entire curve, it actually reaches this point 3 times. So that's what violates this condition here. So it needs to be one-to-one, but it is possible for R of A to equal R of B. That's okay. And the reason that's allowed is because they said it's one-to-one between A and B, not including A and B. So this is not going to meet the definition of simple, because it has to actually cross 3 times: R of A, R of B, and then the third time, right? R of A, second time, R of B. So that second time is not allowed. That's too much to talk about it, but you get the idea, right? So that's what we mean when we talk about simple curves. We're not really going to do much about it. I guess we can do this. Here's an example. They say, is the curve R of t cos t sine 2t over 2 with 0 less than t less than 2 pi a simple closed curve? And probably I say that it's probably not, because I see the 2t here, and I think that's probably going to ruin it. But if we wanted to see whether it does, I mean, maybe we can go and graph it like on Desmos or something. Right, Desmos. Actually, let's go Desmos parametric. Oh, okay. Oh, that's neat. So like if I go here, I can go to, where's pi? Pi. Okay. So we're going to plot a parametric curve, which I just Googled Desmos parametric curve for this. And we'll just change these here. So keyboard, I'm zoomed in. That's a problem. Okay. So if I go here, we're starting out with cosine t, functions, cosine t. Can I get a t? T, close parentheses. Okay, did it. Then for the y value, we want sine 2t over 2. So I'm just going to go 0.5 because I'm lazy. Functions sine 2t, close parentheses. Okay, so obviously we just graphed it right here. And we can see it's simple but not closed. Sorry, closed but not simple. So it has this kind of shape, which is closed but not simple. And you could even prove that it's not simple, because you could just figure out what t values you could plug in to get the same point. So for example, r of 0, if I plug in 0, is cosine 0. sine 0t over 2, which is going to be 1 comma 0. Wait. Yeah, it would be 1 0, but that's not the one I want. Okay. So that's not the one I want. Um, so that was wasted effort. I'm going to redo that. Let us try pi over 2. Oops. Pi over 2. We're going to try pi over 2. If I plug in pi over 2, I got cosine pi over 2, comma, sine 2 times pi over 2, which is cosine of pi over 2 is 0. Sine of 2 times pi over 2 is pi, so sine pi, which is 0, so I get 0, 0. Okay. Then I'm going to put in, let's see, another one. 3 pi over 2. That's going to be cosine 3 pi over 2, sine 2 times 3 pi over 2, cosine 3 pi over 2 is also 0. Sine of 6 pi over 2 is sine of 3 pi, which is also 0. And so you see we got 2 points inside of the interval. So there are 2 points in the open interval 0 to 2 pi with, the same output, 0, 0. So the curve is not 1 to 1. All right, so that's what you'd have to do to mathematically prove that it was not simple, is actually find 2 points where you get the same x and y values there. Or just look at the graph and see that it crosses itself, right? But that's the definition. It says should be 1 to 1 over AB. And if it's not, then it's not simple. As simple as that. Okay, so my advice there is going to be to graph them just like I just did. It would be really easy to tell if something is simple or closed just by looking at the graph, right? So I just Googled parametric curve Desmos and I found this. And this is like an app that somebody made, which is why it's a little bit weird, but easy enough. There's other ways to graph parametric curves as well. Okay, so that's it for curves, really. So the next thing we want to talk about is going to be connected region. Just going to copy paste a different picture for you here. This is going to also make perfect sense, I think. So connected is going to basically mean the region is in one piece. Okay, and simple is going to mean the region has no holes. So with that in mind, of course, you can see exactly what's going on here. If it's simple, there's no holes. If it's connected, then it's in one piece. But in this case, these are connected, but they're not simply connected. I should have said simply connected instead of just simple. So connected, but not simply connected because of the holes. Okay, and there's also a definition here. So connected means for any 2 points, there's a path from the points that stays inside the region. So if you have a point anywhere in here and you have another point anywhere in here, you can connect them without leaving the region. right? And that's also true down here, right? If I put a point in here and I put another point uh, in here, no matter where I put the points, you can always get from P1 to P2 without leaving the region. So they're connected. All of these are connected, but they're not simply connected because simply connected says that any simple closed curve that lies inside D, then the curve can be shrunk continuously to a point while staying inside D. So what that means is this. So like for simply connected, what you'd be looking at is if you make a circle and then you shrink that circle down, right? Then it would shrink down to a single point. And if you shrink that down to a single point, then you don't have to leave the region. And that doesn't work if there's a hole, because if you put the curve around the hole, right, and then you try to shrink it, right, you try to shrink the curve, you're going to end up there. And that is not inside the region, right? This dot here is outside of the region because it's in the hole. Um, so if it's simply connected, you can shrink the curve down to a point without leaving the region. But if there's a hole, you can't do that because when you shrink it, it'll end up in the hole. So that's what it comes down to. That's what the mathematical definitions are, although they don't really say how do you shrink it continuously, but you get the idea, right? Also, I don't have the picture here, but I'll just draw one for you. If I draw shape like this and I shade it, so if I tell you that this is D1 and this is D2, and D1 union D2 is actually what D is, then D is not connected. Because this will fail that first test where you can connect any 2 points by a line, right? Because if you put your first point over here in D1 and you put your second point over here in D2, you can't get from P1 to P2 without leaving D. So that is not connected. All right, so that's simple and connected region. I don't really know if there's any kind of work you can do on those. I mean, maybe they can show you a picture and say, is it simple or connected? Simple, is it connected or simply connected or what? But you can look at it easy enough. Um, okay, excellent. So now what we're going to do is we are going to get into talking about conservative functions, or conservative vector fields, I should say. So let's do this. Um, yeah, conservative vector fields and the fundamental theorem of line integrals. They say for line integrals in your book. I've seen a lot of people say of line integrals. Doesn't really matter. All right, the fundamental theorem for line integrals. I want to make that uppercase. Okay, so what is it? So first of all, what we want to do is we want to talk about what is a conservative vector field. Okay, so this is given to us before. I'm just going to remind you. So definition. If there is a little function f of x, y, z, such that the gradient of f equals capital F, then capital F is called a conservative vector field. Or they called it a gradient field in section 6.1. Okay, so that's your definition of conservative vector field. And there is a theorem, which I think I'll copy paste the theorem, and I actually will prove this one because it's easy. No, I'm just kidding. It's really hard to prove. So you'll be learning a lot if I prove it for you. Oops, that's the wrong theorem. Let me delete this. Not that theorem, that's the wrong theorem. Well, where is it? Line integrals. There it is. Awesome. All right, so this is the fundamental theorem for line integrals right here. And what it's telling you is there's an easier way to do line integrals if you happen to know that your vector field is conservative. So let me just remind you. So this is the idea here. I'm going to remind you of what's going on, and then we'll prove this theorem here and explain it. So reminder from the previous section, right? 6.2. You learned to compute the integral of c over some f dot dr, right? And there were steps involved, right? The first thing you had to do is you had to parameterize c. And then the second thing that you had to do was you were going to have to compute that dr, right? Compute that the dr, which we said was r prime of t dt. And then finally, you could actually evaluate this integral. And the integral was like an integral from a to b of the f. You had to plug in the r. Then you did the dot product with r prime, and then dt. Right? So there were a lot of steps. Okay. So what is different about this theorem is that it gives us an alternative if your vector field is conservative. But if you suppose that f prime is conservative now, then you would know that there was a little f such that gradient f equals big F, right? That's the definition of conservative. So if you knew that big F was conservative for some reason, then you would know about the existence of this other function, little f, okay? And this relationship between them. And basically what this little f does is it acts like an antiderivative. So little f is the antiderivative. Put that in quotes. For big F. Okay, because here's why. If we look at this final integral that we're doing here, right? The integral that you end up with. Here's what you have. Because we know that the integral over c of f dot dr is what we just said we were going to do. Integral from a to b of the capital F dot, I need to write in the stuff, capital F of r dot r prime dt. Okay, that's just what we've already talked about. But capital F, because capital F is conservative, is actually the gradient of little f. Okay. And then it turns out that this bit right here was trying to underline, but I did not. It turns out that this bit right here is actually the derivative of something. Because if you do the derivative with respect to t of f of r of t, what you get is you have to take the derivative of the outside, but there is no just ddt of this function. It's going to be the, it's going to be this gradient f with the r plugged in. And then for the chain rule, you multiply by the derivative of what's inside. Okay, so if you take the derivative with respect to t of f of r, you get the gradient of f of r, and then the chain rule tacks on this derivative at the end. And that's what this is. So this is telling you that you have the integral from a to b of the derivative of f of r dt. But then this is just the integral of a derivative. So when you integrate a derivative, you just get back to the original function, but you've got to plug in your a and your b, and then you end up with f of, r of b. I didn't write r of t there, but r was a function of t. And then minus, if you plug in the a, f of r of a. And so basically what I did here was basically the proof of the fundamental theorem of line integrals here. And the only thing that's really tricky is just figuring out what this is supposed to be. And you kind of would have to convince yourself that this was true, because so let's see here. If you're actually going to take this derivative, right? F is a function of x, y, z, but x is a function of t, y is a function of t, z is a function of t, right? So actually, if you back this up, if you were going to do this derivative ddt of f of r of t, you would have to say, well, that's going to be like the partial of f with respect to x, partial of x with respect to t. That would actually just be dx dt plus partial of f with respect to y, dy dt, partial of f with respect to z, dz dt. And what was I doing with that? Oh, yeah. And then this can be split up into, make it look like two vectors, where one vector is derivative of f with respect to x, derivative of f with respect to y, derivative of f with respect to z, and the other one is the derivative of x with respect to t. I'm kind of mixing my notations here. Derivative of y with respect to t, derivative of z with respect to t, and so I'm just splitting, like this is by the chain rule, right? This chain rule. This was just separating it out and realizing that I could separate the fx, fy, fz here, and the xt, yt, zt here, and just writing it as a dot product because I feel like it. And then this first vector here is gradient f, and this second vector here is r prime, right? Like x, y, and z like are the components of here because you're saying like r by definition is x of t, y of t, z of t. So that's more work than we needed to do, but basically this derivative is this. And so I can back this up here, which is what we ended up with, to this line, which is the first line. So this is equal to this. Okay, that's too much. But you get I think you get the idea. So you can convince yourself that this is actually this, and this is the critical step because now this is the integral of a derivative, which just basically cancel each other out. But you have to, well, I shouldn't say they cancel each other out. The antiderivative of a derivative is just whatever you have in there. So the antiderivative of d dt f of r is f of r. And then you plug in your limits of integration. All right, very complicated sounding. I made it way worse than it is, but that is what this says. Gradient f dr is f of r of b minus f of r of a. And by convention here, this is the capital F. That's what's going on. Okay, so that is the fundamental theorem of line integrals. And I basically proved it. That's not how you use it, okay? So that's the proof, essentially. Using it is much easier. Why is it much easier? It skips those steps with parameterizing and everything else. Okay, so it skips all of the steps of actually solving this in the normal way. So let us prove that. Okay. All right. So here's an example. Suppose I tell you so suppose you know already that the gradient of what function? Let's say the gradient of x squared ln y plus yz squared is equal to, looking for the function here, not actually going to integrate it myself. Suppose that's actually equal to 2x ln y comma x squared over y plus z squared comma 2yz. I guess that wouldn't have been too hard to do, but okay. So suppose we already know this. Okay, so what we're saying is that the vector field on the right, this is a vector field. This is your f, and it is conservative. And I know it is conservative because it is the gradient of some little f. Okay, so that's what's going on. The gradient of the little f is equal to the big F. Okay, now with that in mind, what I want you to do is I want you to compute this. So now compute the integral over c of f dot dr, where r of t is going to be giving you the c is given by r of t, which is equal to t squared comma t, where 1 is less than or equal to t, which is less than or equal to e. Okay, so to actually apply this theorem, let's figure out what our integral is. Okay, so this is the problem. So let's get started on the work. So I'm given the big F, I'm given the little f, I'm given the c, and we're supposed to be calculating this, right? So let's start with the thing we're supposed to calculate. So the integral over c of f dot dr is the integral, I'll say over c, of f. Where's the f though? The f is 2x ln y minus x squared over y plus z squared, comma 2yz. That needs to be with the dr, dotted with the dr, and we also need the parameterization of c and so on, right? This is what we're supposed to do. But you don't actually have to do that because the fundamental theorem says this. By the fundamental theorem, this is actually, well, it depends on how far you want to write this. So you don't need to write this step, but I am to try to explain. So you don't usually write this. You don't usually write this line. But the integral would be your a and your b, which are 1 and e. 1, e. This is your capital F, right? But your capital F is actually the gradient of the little f. So the gradient of the little f, which is x squared ln y plus yz squared, and then dot dr, and right. So this is the big F, this is the gradient of the little f, and these are the a and the b's, right? So all you have to do is you have to basically do this. It's going to be this function here, x ln y plus yz squared. And basically what you do for your limits of integration is they go from r of 1 to r of e. And the reason it's r of 1 and r of e and not 1 and e is because if you think about it here, these limits 1 and e are for t, right? Those are limits for the variable t equals 1, t equals e. But this function has x's, y's, and z's. So in order to get the x and the y and the z, you're actually going to have to plug the 1 and plug the e into your r. There's the x, there's the y, there's the z. That's where the x, y, and z come from. Okay, and that's also, I mean, written in the theorem, of course, because, right, into the f you plug r of b, not b. Okay, so like I said, you don't usually write this line. You can kind of jump to here. And then I'm just going to rewrite this one more time so I can duplicate. I'm actually going to erase these. And I'll put the x, y, and the z there. And I'll put the x, y, and the z there. So like if you plug in r, if you plug 1 into r is up here, t squared tt, right? So you end up with 1 squared 1, 1, which is 1, 1, 1. So that's your bottom limit is 1, 1, 1. And then for your top limit, that's r of e, which is going to be e squared e squared e, and then you just plug those in. So you go x squared ln y plus y z squared. Do the same thing with the 1 squared ln 1 plus 1 times 1 squared. You work this all out. This is e to the fourth. Ln e is 1 plus e times e squared is e to the 3. Ln 1 is 0, so this is 0, so minus 0. And then plus 1, but it's minus plus 1. So it is e to the fourth plus e to the 3 minus 1. And that involved no parameterizing the curve. There was no gradients to calculate. There was nothing, right? So we get the answer with no parameterization, gradients, or anything. You just have to know what the little f is. You have to know what the little f is, and the a and the b. So the f, the r, the a, and the b, that's all you need to know. And then it's like you get to use the little f like it's the antiderivative of what you start with, right? This is the big F, this is the little f. So it's like the little f is the antiderivative of the big F, which is the opposite of calculus 1. Okay? So it saves you a lot of trouble. So we're going to do one more of these just to hopefully convince ourselves that we know what we're doing. Less explanation here. So given little f of x, y, two variables, that's nice. X minus 1 squared y plus 1 squared x is a potential function, right? Sometimes they use the language, the vocabulary. Potential function for capital F equals 2xy minus 2y plus y plus 1 squared, comma, x minus 1 squared plus 2yx plus 2x. Calculate the integral over c of capital F dot dr, where c is the lower half of the unit circle oriented counterclockwise. All right, now we could draw this. They do give us a picture, so I'm just going to go steal the picture from the book real quick. Well, where is it? Up, I guess. Nope. Oh, here it is. Copy. So there's the curve C is the lower half of the unit circle, and they say oriented counterclockwise, which, do I see an arrow on here? I don't, but the arrow is counterclockwise is this way. right? Now, one thing you can do here that's useful is before you start is if this is the direction that we're going, right, then that automatically means that this point right here is the R of A, that's the starting point, and this point right here is where you end up, is the R of B. Okay, so in this case, R of A, you actually know exactly what it is. It's the point -1 comma 0, right? And the R of B, that's where we end up, um, that's at 1 comma 0. So you don't actually have to parameterize that curve at all. You just need to know where the curve starts and where the curve ends. That's all we're really doing here when we like when we went from here to here, we got these points. That was just calculating the starting point and the ending point. And you don't need to calculate them with a formula if you've got a picture and they're labeled on the picture, starting point, ending point. Okay? Uh, with that said, let's go ahead and let's do this integral now. So um, I recommend that you don't write nearly as much as what I wrote on the other one. Here's what you should write. So here's our work for actually doing this now. Um, so we're supposed to be calculating the integral over C of f dot dr. But we know that f has potential function little f, right? And that means big F is conservative. So the fundamental theorem tells you that your integral is just little f evaluated from R of A to R of B. That's it. Okay. That's the fundamental theorem of line integrals. We just applied it, right? This is fundamental theorem. Notice that I'm not like writing in anything yet because it would just be a waste. Like why bother writing out what capital F is? We don't care. I know that the way you do this is capital F will go to little f here, and then we plug in the endpoints. Once I write this, now I substitute stuff in. What is the little f? Little f is the potential function. It's given, right here. This duplicate, that's the little f. So we're just evaluating this function. Right, that's little f. And then we're supposed to be evaluating it between R of A and R of B. We never even came up with an A and a B, but we know the starting and ending points. So what's the ending point? Or what's the starting point, I should say? The starting point is right here. R of A is -1, 0. R of B is 1, 0. So -1, 0 on bottom, 1, 0 on top. And then we just plug those in. So we just plug them in. So we plug in the 1, 0. So we're going to get 1 minus 1 squared times y, which is 0, plus y plus 1, which is going to be 0 plus 1 squared times x, which is 1, minus, plug in -1, 0. So that's -1 minus 1 squared times 0, plus y plus 1, which is 0 plus 1 squared times x, which is -1. And then you just work all this out. So what do we got? We got 0. This is 1 times 1, which is 1, minus, this is -2 times 0, so 0. And this is 1 squared, 1 squared, which is 1 times -1, which is -1. So I get 1 minus minus 1, so I guess the answer is 2, I hope. Okay, so look how quick we did this, right? You just go from the integral to what the fundamental theorem for line integral says. This you should remember. From there, just plug in what your little f is. That's the potential function. And you need to know your ending point and your starting point for the curve. Okay? Ending point, starting point for the curve. Okay? And that's it. You plug them in and you get an answer. Very easy. Okay? Now what we want to say is this. So we should have noticed this from our two examples. Independence of the path. And so basically, here's the idea. Um, when you use the fundamental theorem, integral over c of capital F dot dr, and you get that it is little f evaluated between r of a, r of b, the starting point and the end points, or I'm not going to write it out in more detail than that. The curve doesn't matter. It's just the starting point and the ending point, right? The r of a and the r of b are the starting point of the curve and the ending point of the curve. We don't use any of the rest of the curve. You only use the starting and ending point of the curve, right? Because the curve is the whole curve, but it starts somewhere, and that's r of a, and it ends somewhere, and that's r of b, and we don't care about what it does in between. You only use the starting and ending points of the curve. The rest of the curve doesn't matter. That means that the integral of c1 of f dot dr equals the integral of c2 f dot dr. This is only for a conservative f. Right? Because the theorem, fundamental theorem, only applied to conservative functions. So these two curves are equal, provided they have the same r of a and r of b. Right? So what that means is if you're looking at the xy plane, or 3 dimensions, it doesn't matter. If you've got a curve like this, so if we have, r of b here, and you have r of a over here, then you could have one curve do this, that could be c1, and you could have another curve do this, that could be c2, and it doesn't matter, the integrals are the same. Because when you apply the fundamental theorem, the only thing you're going to use is the starting point and the ending point, not the rest of the curve. Okay, so what that's telling you is we say that the integral, line integral of a conservative vector field line integral of a conservative vector field is independent of the path. The actual curve itself does not matter. We only care about the starting and the ending point. Let me see if I can find that definition. Maybe here? Yeah. All right. So here's some actual book definitions of this stuff. So first of all, they kind of separated this out here. First, they said, what does it mean to be independent of path? They say path independent if the integral over one curve equals the integral over the second curve, as long as they have the same initial and terminal points, right? Initial was the f, no, the initial was the r of a, and the terminal was the r of b. Okay. And then in a theorem, they say if f is conservative, then f is independent of the path. Okay. I wouldn't really say that the vector field is independent of the path. That's a weird way to word it. I would say that the line integral is independent of the path. So it's weird. They're using a weird way to state that, but the idea is that the integral, well, we already said it several times, right? The curve doesn't matter, only the starting and ending point. Okay. And then they give you a picture that looks just like the one that I already drew. This one. Okay. Except they drew a vector field on it. So you can just imagine some vectors on here. Okay. So there we go. That's nice. And then there is a actual important consequence of this. So an important consequence is this. So if we think about what this is talking about, then what this is also saying is, I'm going to say closed paths, or closed curves. So if C is a closed curve, then I'll say a closed curve will be wordy here. If C is a closed curve with parameterization R of t, where t is in between A and B, then R of A equals R of B. I should say closed simple curve, right? I guess it actually doesn't matter, but I'm going to say closed simple curve. So closed simple curve with parameterization R of t with A less than t less than B, then R of A equals R of B, right? So the line integral of a conservative f with potential function little f is, so if you do the integral over a closed curve of the capital F dot dr, right? We know that the fundamental theorem says now that this is going to be the little f evaluated between R of A and R of B. But those are the same because you're going to get f of R of B minus f of R of A, but these are going to be the same because this and this are the same. So when you subtract them, you're going to get 0, always. Okay. So that's going to happen anytime. Okay. Now, having written that out, I want to maybe state it a little bit more here. Hold on. I don't know if I copy pasted the right thing here. What's this? No, that's not what I want. Okay. So you always get 0 here for a closed curve. And then I want a little bit of vocabulary related to this. So um, some vocab stuff. Okay. So first is this. So a line integral of a vector field f over a closed curve C is called the circulation of f over C. Okay, so the key there is the word circulation. That's a new word. Okay. Um, they often will write the integral slightly differently if it's a closed curve. They don't have to, but they will often write the integral over a closed curve like this. So normally we've been writing integral over C of f dot dr, right? Well, what they'll do is they still write the exact same stuff, but then if you know that it's curved, they do this. They just put a little circle there to indicate that the curve is closed. So you'll see this um, in other textbooks and things. You don't really have to pay any attention to that, really, right? They're just telling you that the curve is closed, which maybe you care about and maybe you don't. But there you go. So that's the thing you want to pay attention to there. The circle indicates it's closed. Doesn't matter if you do or if you don't. And then anyway, if you combine the idea of the word circulation, well, actually, I was going to say what that means for conservative vector fields, but I want to say one more thing about circulation, which is how you interpret it. So the interpretation of the circulation of f over c is it's a measurement of the tendency. So the integral over c of f dot r, that's circulation, is the tendency How do you spell tendency? Is it impossible? It's got an E, right? Why did I put an A? Tendency. Is it's the tendency word's hard, sorry. I want to get the wording right. But basically it's the tendency of the fluid to go in a circle around the point. Is what I'm trying to say, but I'm trying to use the correct words here, which is why I'm not Googling it, but I'm trying to find it. Okay. So the tendency of a fluid to move in the direction of C. So let me draw a picture. So right? You could have, so like you have some kind of vector field, right? And I'm just kind of filling it out right now. Um, okay, so let's say you just have some vector field f, right? And then if you put a curve C in here, so like this, it doesn't have to be a circle, but like, so if you put a circle in there right there, then you can kind of see that what's going on here is I drew the like the vector field lines as sort of going around clockwise, right? And also the curve here is going around clockwise. So the vector field has a tendency to go along the same direction as that curve there, right? And that is what the circulation is measuring. So how likely is it for likely, but how much is the vector field following the curve? That's what you're measuring when you're doing a line integral like this. And so that's why they call it circulation, right? Because this is a circle and the vector field may be going in a circle or maybe not. Maybe it's the opposite direction. Maybe it's straight through the curve, whatever it's doing. And so the line integral circulation is going to be measuring the tendency to follow that circular curve. Okay. That's why they use the word circulation. But yeah. Now, what was the point of that? Well, the point of that, and that's provided the vector field F is like the flow of a fluid. Maybe I'll say that. Fluid velocity, maybe. Okay. So anyway, that's what circulation, the idea of circulation is. And then you can bring it together with the idea of conservative vector field. So you could say, so for a conservative vector field, F, the circulation is always zero, right? Wouldn't that make sense? Because the integral around any closed curve of f dot dr is just zero, always. So you'd see the advantage of using that symbol there. It doesn't really do anything, but I can just draw the little circle and I'm saying that C is closed. And I know that the integral of a closed around a closed circle for a conservative vector field is going to be zero by the theorem that we set up here. Okay, so those are just kind of little happy facts, I guess. You don't need to do too much with them, I think, but yeah. There's one more thing here, which is going to be, I think, probably calculating potential functions. But let me scroll down a little bit. We talked about path independence. Um, I guess technically this is a separate theorem. Let me put it in. Where is it? There it is. Here's a theorem. Um, this theorem says if f, I hate it when it does that. If f is continuous vector field that is independent of the path and the domain of f is open and connected, then f is conservative. Now you might read that and feel like it's what we just talked about up here, where I said, you know, f is simple closed curve, blah blah blah, and we just showed that the wait, no, sorry. You might think it's the same theorem as this, which is the vector field is independent of the path. Sorry, here. If f is conservative, then f is independent of the path, right? You have this one. If f is conservative, then f is independent of the path. That one we got for free just from the fact that the fundamental theorem of line integral says so. The theorem that we wrote on the bottom is not the same thing, because this is if conservative, then independent. This theorem is if independent, then conservative, right? So that's the opposite form of the same theorem, right? The converse, right? So we had two theorems. If f conservative, then f independent of path. This one says converse, if f independent of path, then f is conservative. Okay, now how are you going to prove that something is independent of the path? You're probably not. So you're not probably going to be using that theorem, if f is independent of the path, then f is a conservative. You're probably going to be doing it the opposite way. So the way you'll be doing this is probably like this. So the way you might use this is to show a vector field is not conservative by integrating over two curves with same starting and ending points, and getting different values. Right? So we might use the theorem that way. So you might use it to show that a function is not conservative. Now I wouldn't I wouldn't be doing it that way, but technically you can do that. Okay. So in fact, since I said I wouldn't do it, I'm not going to do it. What we are going to talk about is potential functions. And this is how I would generally show that a vector field is not conservative, because I think I can usually try to find, we can usually try to find a potential function. All right. So one thing I will say is you should see the 6.1 lecture for some examples, because we did it there. Oops, not quite what I wanted. What I did want is I wanted to distill their problem solving strategy for this. Because we did this in the previous section, but make bigger. Okay, good. Good enough. Done. Save to photo. Come on. Open up. Okay. So let's go find that picture that I just saved. And here we go. So this is our strategy. So remember that what you're going to be doing is basically integrating to get back to the original function, right? So let me just write the idea. You have a vector field. like what do we say? Capital F. They say PQ. Okay. Now, if it's conservative, then it has a potential function, right? If it's conservative, then um, F, which is PQ, is actually the derivative of some little f and the derivative of some little y, right? Because it's the gradient of a function. Um, so to get back to f, you use that little f is going to be the integral of p with respect to x, and little f is also the integral over of q with respect to y, because p, which is little f of x, is a derivative with respect to x. So if we integrate with respect to x, we'll be getting back to the original function. That's the idea, right? And then they explain what to do here. And then they say, like, integrate p with respect to x. The results in a function where you get an answer for, they say g for some reason, plus a constant, but the constant is a function of the other variable. So when you integrate with respect to x, you don't get a plus c, you get like plus constant of y. Then you do what? Well, that's very complicated. That's not the method that I used. Hold on. Right. So we do that, then we take the derivative, then use the equation gy equals q to find the h prime. Then you integrate h prime y. Okay. Yeah. All right. Yeah, you can follow that method. Their method's fine. Of course, it's fine, right? The text, but it's not necessarily what I would do. Um, I'm going to pick this one here. Okay. Example. We're going to find a potential function for f of, sure, they said f of xy, but then they put xyz. So that's not cool. No, you can't do that. Your problem's all messed up, guys. Very strange. Their example, they say it's a function of two variables, and then it's got three, and then they do it like it's only got two. It's just very strange. I'm looking for potential or a function with two. Okay. Okay, good. Yeah. All right. So this is off the actual homework here. So f is going to be negative y plus e to the x sine y I, and then j, but I'm writing it in the other notation, x plus 2 e to the x cosine y. Okay, so the method that I used was not quite the same as the one that's listed here, because the one that's listed here is a little bit rambling to me. Like, you start out with p, you integrate p, you get this thing. Then they say you take this and you take the derivative of it with respect to y. And whatever you get should match the q. So whatever you get from that derivative should be q. But then they're saying you figure out what that h prime is, and you integrate it to get h, and then you put it all together. That just feels weird to me. It's fine. I just don't like it. Here's how I would do it. So, I mean, I would do it the way that I wrote here, basically, though. I would just integrate twice here. Once for p, once for q, and we'll look at the results. Okay. So these are my steps. So integrate p integral p dx and integral q dy to find two possibilities for f. Okay, so let's do that. So you just do integral negative y plus e to the x sine y dx. And that is what f is equal to. So we just do this integral. And this integral with respect to x is not going to be hard. The integral of negative y dx is negative yx. Here on the second term, e to the x sine y, the antiderivative of e to the x is e to the x. So we get plus e to the x sine y. And there's my antiderivative. But then you add this extra constant, and that constant can have any amount of y's in it. Because anything that just had a y in it, if you took the derivative of this with respect to x, would just disappear, which is why you don't see it here. Do the same thing for the q, which is x plus 2 e to the x cosine y dy. So we're doing the integral with respect to y this time. So the only place there is a y is just cosine y dy. So the antiderivative of cosine y is sine y. So this is just x plus 2 e to the x sine y. And then plus another function, c2, that could have any number of x's in it. And then what I do here is, this is just for this problem because of the way it's written. I should just multiply this out just so we can look at it better. So this is, if I distribute the x and the 2 here, you have x e to the x sine y. And then if you multiply the 2 here, you have plus 2 e to the x sine y, and then plus your c2 of x. Okay? Then, wait, hold on. I feel like they made a mistake here. This one doesn't have a potential function. Dang it. Okay. We're going to see why in a second here, if possible. Okay. So then what you would do is this. So if you look at your results, so I've got f of xy is supposed to be negative yx plus e to the x sine y plus constant that has only y's. And then for the other one, f of xy is also supposed to be equal to x e to the x sine y plus 2 e to the x sine y plus this c2 of y. And the thing is that these are supposed to be consistent here. And they aren't. And I will explain why they aren't right now. So here's why they aren't. So some of the terms are in both of these, right? Wait, did I write this properly? X e to the x, e to the x. Yeah, actually none of them are here. So the problem is that you have like this term and you have this term, right? Where are those terms down here? Because they should be on the list. And they aren't. right? Like where's the negative yx? Well, negative yx is not this term. Negative yx is not this term. Negative yx can't be here because this is a function of y only, and this is yx. Oh, also, wait, I wrote that wrong. This should have been x. But the same thing holds. Negative yx is not a function just of x. So already these are not consistent to each other, right? Because there's a term in the first one, right? Term negative yx is not in the second function for f. Right? Because negative yx obviously is not x e to the x sine y, but also negative yx is not 2e to the x sine y, but also negative yx can't be the c2 of x, right? If it could go in c2 of x, it'd be fine. But the problem is that c2 of x is only got x's in it, not y's. So this can't be part of this. So the negative yx can't be, it's not a here at all. It's not here, not here, not here. And there's other problems as well, right? Like you could say like, well, what about this one? Where is it in the first equation? Well, this is not negative yx. This is not e to the x sine y. It almost is, right? Like this is, but this has got a 2. This doesn't have a 2. So this is not this. And also 2e to the x sine y is not part of here because this is a function of y only and this has x's. So that's another problem, right? And there's lots of other problems here. So this is just not a conservative, just not a conservative vector field, okay? Because you can't do this. Basically, if you try to follow our method for coming up with a potential function and you can't, then it's not conservative. So just not conservative. No potential exists and f is not conservative. All right. Well, we need one that is conservative here. That would help. I'm trying to look at one and let's see if it is. That would just be a 1/2. We create that with respect to y. We're not going to get the 1/2, so that's not conservative. Well, why? I think this one is. So I'm trying to find one. I hope this one is. We're going to do this one. Um, if possible, find the potential function for I'm just thinking again, sorry. Yeah. Okay, well, that's fine. I was trying to find a harder one, but maybe I should just find one that we can do rather than worry about whether it's easy or hard. Okay, try again. So, I mean, we're still going to be doing the same exact procedure though. So what we're going to do is we're going to uh, find that the f, which should be the integral of p dx, and f, which should also be the integral of q dy. So we'll do those. So f should be the integral of y e to the x plus sine y with respect to x. So we just do this integral. So we do the integral with respect to x. The antiderivative of y e to the x is y e to the x. The antiderivative of sine y dx, we're treating the sine y as a constant, so it's going to be x sine y. And then plus a constant, and that constant could have any number of y's in it because it's not really a constant. I'm going to move this over here, actually. Okay. Now do the same thing for the other one. So we want the f is going to be the integral of e to the x plus x cosine y dy. So now we're integrating with respect to y. So the integral of e to the x dy is y e to the x. The integral of x cosine y with respect to y, well, the antiderivative of cosine y is sine y. So this is x sine y plus a constant that is a function of x. Okay, so then what you do is you write these out. How did I refer to it last time? I said, look at the results. Okay, look at results. So I've got f equals y e to the x plus x sine y plus c1 of y. And the other one is y e to the x plus x sine y plus c2 of x. And this time, everything's good when you try to combine them into 1f if they're consistent. Okay, so f equals, right? So the idea here is we don't have the problem that we had last time, right? You look up here and you say there's y e to the x, and you say, well, where is it down here? Right here, right? Matches up perfectly. And then you say, okay, well, what about x sine y? Where is that in the bottom function? Oh, it's right here. Oh, well, that's it, right? Those were the only two pieces that we saw. So you just take all of them, you take every piece of the function that occurred at least one time into the f. So it's y e to the x plus x sine y, and then plus a real constant. So each piece, each term basically that appeared in either should appear here. Should appear. So each term should appear in the final answer. Okay. Now, the reason I say each term from the two f's should appear in the final answer, but we didn't do that up here, remember, was that the issue here, the issue here is that these couldn't possibly be the coming from the same f, because like this function right here, it needs to be somewhere down here, either here or here or here. It can be part of here, that's okay, but it can't be because this is yx and this has got to be only x's. So you can't just plug that in there. So this term is not part of a real f because it would have to be on this list somewhere, here, here, or here. Whereas here, this is here, and there are no other terms. So there's no issues. And I couldn't really find one where the results didn't match. Yeah, I think that's it. I can't really find one. So that's going to be it as far as finding a potential function. You saw one where it happened, and you saw one where it did not happen. Um, and you saw that my method was not quite what the official method was in your book. So I think that's it. I have to do another lecture on 6.2 where I do some more line integrals, like applications. And if I find, I'll find a better potential function example to show you at that time. But I think that's it for now. So what did we do? We did finding a potential function. That's last. We did path independence. Basically, conservative vector fields have the property of path independence. We just mentioned the word circulation and kind of what it was. It was the tendency of a fluid to move in the direction of the curve, but it's just a line integral, but we're calling it circulation. If you have a conservative vector field, then the line integral around any closed curve is 0 because you have the same starting and ending point. And that's important because the fundamental theorem of line integrals says that the only thing we care about when you're integrating a conservative vector field is the ending point and the starting point. That's it. That's what it means to be independent of the path. We did examples of applying the fundamental theorem, and this should be your main example here, right? This is an entire line integral, and it's way, way, way shorter than what we did in the previous section. That's why we like it, okay? So you do these with this method if you can, but you can only use this method for conservative vector fields. That's the trade-off, right? It's a shorter method, but it doesn't work on any vector field. It only works on a conservative vector field. All right, I think that's it. So good luck on the homework. Get started on it early, I hope. Come to office hours.